All right, thank you very much. It's a pleasure to be here. It's my first time in KITP, and I'm really enjoying it. So that's my title, Finite-N holography. The subtitle, supersymmetry and modularity in gravity. That should become clear in the very next slide. Throughout this talk, by holography, I would mostly mean ADS CFT. And N, as usual, measures the number of degrees of freedom of the CFT. And in the dual ADS, the Newton's coupling constant, the gravitational constant, scales as an inverse power of n, 1 over n squared, for example. And the main question is, can we make sense of the gravitational functional integral at finite n? Yeah. So when n is infinite, then we know that there's some saddle point approximation, and classical gravity is valid. So 1 over n means quantum gravitational effects. And the class of observables I'll be talking about is of this sort, the generalized partition functions depending on external chemical potentials mu, which couple to conserved charges q. Okay. So in the CFT, these traces make perfect sense at finite n, and we expect by ADS CFT that this is equal to some gravitational partition function. Okay. So here we don't have a good notion of a Hilbert space in gravity. So what we usually do is think of it as a functional integral and expand it in terms of saddles, and around each saddle you write some kind of quantum effective action. Okay. Now what I want to posit is that when this trace is a supersymmetric index, namely there's a minus 1 to the f, then there's an independent definition of this gravitational path integral, which can be calculated. And so this is what I want to discuss today. And the way it works is fairly conservative. So it's the same structure that you see here. So supersymmetry allows for sort of an all orders 1 over n expansion, which then can be summed into some function. And then there's a question of what are all the saddles which are allowed? This is a non-perturbative question from this point of view. And some other structure, the examples that I show you, it will be modular symmetry or modular-like symmetry to fix these saddles. Okay, so that's according to the theme of this conference, that there are the supersymmetry algebra and the modular symmetry algebra, which tells you something about the gravity. Okay, modular symmetry is SL2Z is a set of symmetries of the torus. So my main example will be ADS2 CFT1, which is relevant for the near horizon geometry of supersymmetric black holes. And in this case, I'll discuss the observable. So one expects that this supersymmetric black hole is some independent quantum system. So the first question you can ask about the quantum properties is what's the dimension of the Hilbert space. So that will be the calculation. This is based on so older work with Atish Dabholkar, João Gomes, and some more recent progress, which is why I'm giving this talk, with Luca Eliesiu and Joaquin Turiachi, who are both here in the audience. Okay. So I'll discuss this for most of the talk, and then at the very end, I'll just sketch how there is a very similar structure in higher dimensional CFTs, ADS CFTs. Okay. So why do we expect that there is a gravitational definition of the index? Well, firstly, if you look at the CFT definition of the index, we know it's protected, and therefore it must be equal, it must be the same all the way at strong coupling. Okay? So whether or not we have a gravitational definition, we know that there is something there, and we know what its value is. Okay? So this is, of course, it's not logical, it's just aesthetic. And we expect there is something of this sort, so an integral over the space of gravitational configurations. But now this should be supersymmetric, so it should give fermions some supersymmetric boundary conditions. Now just giving fermions supersymmetric boundary conditions doesn't magically solve all the problems of the quantum gravitational integral. Okay? So one has to do something else. And in field theory, we know we can actually go a little bit further. We know that so imagine the simplest context where there's one supercharge in your theory. So Q square is H. H is some bosonic generator. That's your algebra. We know that the supersymmetric path integrals in field theory localizes onto the space of fixed points of the supercharge. Okay. The formal argument is that you look at the functional integral and divide the sort of space of fields into orbits of generators of this algebra, and at the generic point, the fermionic, the Grassmann integral gives you 0 unless you're at a fixed point. Okay, so the more physical way to say this is that if you have a non-supersymmetric configuration, it breaks more supersymmetry, so the Goldsteiny modes, and that kills the path integral. Okay. So in supersymmetric field theory, we know you get sort of very nice answers. The field theory is localized onto the space of fixed points of the supercharge. Then you have to evaluate the action of the theory on the space of solutions, calculate some one-loop determinant of the non-BPS configurations, and so on. And this has led to a lot of progress in many examples like this. Now you can follow your nose and try to do the same thing with gravity, and you'll get something like this. You'll get an integral over the space of solutions of the variations, fixed points of the gravitino variations, and then you have some gravitational action which you have to evaluate there and calculate some one-loop determinants. Okay. Now this is also not yet a definition because there are lots of problems here which I'm going to tell you about. But already this is a much smaller integral than that, and I want to think of this as a potential definition of the index. Just start with the localized path integral and try to make sense of it and take that as a definition. Okay? And what I want to say is that in the moduli space of ADS CFT, there is this object called the index, which has independent definitions in the local variables which you can calculate. That's the picture that I want to develop. Okay. Now this integral also has many problems. I mean, there are practical problems, but like of implementation. But even formally, there are problems. So, what is the gravitational action? So, there's some infinite derivative expansion, things like this. But today I want to discuss one problem which I think is important, which has at least some kind of a resolution, which may be sort of useful in other situations. I've often noticed that there's something lacking which this might fill. Okay? And the problem is that to begin to talk about such a localization, you need this supersymmetry algebra. So this is a global supersymmetry and a global bosonic symmetry, and you need such an algebra. And the question is, how do you define such a global supersymmetry in a theory of supergravity? So what is the problem? The problem, so at a zeroth level, you can say, well, gravity doesn't have any global symmetries. Or if you pick up a book on supergravity, you'll see the line saying that all symmetries in supergravity are gauge symmetries, including supersymmetry. Okay? Of course, we know very well that these statements are wrong, especially when you have some kind of an asymptotic boundary, like what we want. You have some ADS space. Then you have the notion of asymptotic symmetries or large gauge transformations, and these are genuine global symmetries of the theory. Okay? So there's no philosophical problem. The question is really how to implement these symmetries on the quantum fluctuations of the gravitons. Okay? And so why is this an issue? Well, let's try to think about it. So you have think of sort of pulling the boundary symmetries all the way into the bulk with some vacuum ADS. And there, the supersymmetry and this bosonic symmetry, just an isometry. Okay, those are global symmetries. So you want to implement these background symmetries on the fluctuations. So that sounds like the background field quantization method. The problem is that the background field quantization had not really been worked out until recently for theories of supergravity. And the issue is that the gauge algebra of supergravity is what is called a soft algebra. What that means is that the structure constants of the algebra are not constants, they're field dependent functions. Yeah? And that creates problems, as I'll show you. Okay, so in the next few slides, I want to just sketch this argument of how this is done. It's a very general method. So the context is the usual BRST quantization. So there's some set of fields, phi, think of this as the gravitational fields, some set of gauge symmetry transformations R, and some parameters C. And these transformations obey constraints. So there's a closure relation that defines for you these structure functions. So in Yang-Mills theory, this is really the structure constants of the gauge group. Okay? And then these structure functions obey what is called the Jacobi identity. In all these equations, the multiplication should be thought of as a wedge product, some anti-symmetrization there. Okay? So again, when these are constants, you don't have a right-hand side. That's the usual Jacobi identity that we know. Okay, so this is a more general framework, but this is also fairly well known. And once you have this, you can do BRST quantization. You say you replace this C, the parameter of transformation, by a ghost, and then you have to say what is delta of the ghost that has the structure FCC, and then you can check easily that this is a nilpotent algebra. All right. And then once you have this BRST current, you can also build the Lagrangian. You have some classical gauge invariant Lagrangian, you have some gauge fixing term, and then you can do your quantization. All right. So, excuse me. Now, we want to split the fields into some background part plus a quantum part. This is as in the background, classical background field method. Okay, so circle is the background and tilde means the fluctuation. So now, as we all know, there are two sets of gauge transformations. There's the background transformations and the what are called the gauge or the quantum transformations. Okay, so the the quantum transformations don't act on the background; they only act on the fluctuations. And the background symmetry transformations act on the background as well as on the fluctuations. Okay. Now, I mean, we've all seen this in the context of Yang-Mills theory for sure. So this, for instance, you can see in the textbook of Peskin and Schroeder. Okay. But all of this so far is still a gauge symmetry. And so you should introduce two sets of ghosts. Usually this is not done, but you can do it. In fact, Weinberg's textbook does that. He introduces two sets of ghosts, one for the background gauge symmetry and one for the quantum gauge symmetry. But in Weinberg's textbook, for instance, he introduced two sets of ghosts, and in the very next page, he puts the background ghost to 0. He doesn't so utilize the full power. But anyway, you can do this, and because there's a closed algebra, you have the usual BRST variation. Okay. Okay. Now we want to do something. We want to freeze the background fields to some values. So these are the fields. So think of this as freezing the background metric to ADS space. Okay. That in this language should be thought of as a partial gauge fixing. Right? And therefore, the ghost associated with that background symmetry should be set to 0 because you've gauge fixed. Okay? So these terms, since you've set phi circle to some constant value, this term should go to 0. But as you see here, you can either set C circle, the background goes to 0, or if you can have an isometry. So if R times C is 0, then you don't need C circle, the background goes to be 0. So R times C is 0 means that the background gauge transformation is actually an isometry, it doesn't change anything. Okay? In that case, the background ghost can get a wave. Okay? And notice that if you want a wave, then you must have a bosonic ghost and therefore a fermionic transformation. You can see where I'm going. So these are allowed when you have background supersymmetry, supergravity, local supersymmetry transformations. Okay? In that case, these ghosts, background ghosts, are nothing but the Killing spinors. They're the bosonic ghosts. Okay. So far, so good. And now we want to deform this theory, okay, this algebra. You want to deform this algebra, and you do that by setting, because you've set C circle to some constant value, you deform this so far as BRST, and you set this to 0. Okay. Now you have a deformation. Notice, by the way, that in the ADS context, these background ghosts are non-normalizable, as they should be because they act on the boundary. Okay, they're transformations. Okay, so you do this deformation, and what you get is that you just work out what the symmetry transformations are, and you find that instead of the BRST symmetry, you have this equivariant symmetry. Okay. So with the BRST symmetry, you could have also try to localize, but that's basically useless. You're just saying the integral localizes onto the space of physical configurations. That's not practically useful. Here you use this is not BRST anymore. It's really some supersymmetry. Okay? And the algebra that you get is that it squares to bosonic symmetry, which is kind of the square of this Killing spinor, which is a Killing vector. So more generally, you have an algebra of the following type. You have Q square, so Q squares to sort of all the background bosonic symmetries that are allowed with sort of parameters determined by the gauge algebra. So you can have some sort of translation, rotation, R symmetry, anything like that is allowed. Okay. So this is what we worked out The general formalism was worked out in this paper with Bernard Duvet and Valentin Heiss. And then you could, the nice thing, so for instance, if you want to, many of us have also seen the following problem. If you take a fixed background metric but curved, you ask, how do you write supersymmetry transformation in that? Okay, so metric is constant. That's also slightly non-trivial, but the way usually to do it is you just demand that Q square equals H as an algebra without any additional gauge transformation, and that fixes all the variations for you. But when you have the gravity metric itself fluctuating, that becomes very hairy. This is a very elegant way to calculate the full nonlinear set of transformations. Okay, so we work this out, for instance, for supergravity in this paper with Imtag Jeon. Okay, so that's a brief review of this, and now I want to apply this to the supersymmetric black hole. Any questions about this so far? Okay. So now we have the following situation. So we want to apply this to the supersymmetric black hole. You should think of the black hole as being embedded in some asymptotic space, either flat space or ADS space. Okay. And from the bottom line, the practical sort of takeoff from what I told you so far is that you fix some boundary conditions in this asymptotic space, and you allow for all metric configurations which allow for any killing spinor such that asymptotically it's equal to the background killing spinor and background superalgebra. Okay, so that's how I should now think of this path integral. And the issue is that when you have a supersymmetric black hole solution, you have an infinite tube in the interior, in the Euclidean theory, and that action is infinite. So it's like a singular configuration. That singularity shows up in many different calculations. Like you see that there's no variation of principle, no thermodynamics. Okay? So clearly that there's something wrong about this infinite tube, and you need to regulate it. And in this paper, with Alejandro Cabo Bisset and Davide Cassani and Dario Martelli, in the context of ADS5 black holes, we solved this. We showed how that there is a class of solutions which can be thought of as the deformations of the supersymmetric black hole, which do allow for killing spinors, but they're non-extremal, so they're capped, so they have finite action. That if you work with supergravity solutions, that sounds wrong, because somehow usually if you impose enough symmetry, the black hole is the unique solution. What gives is the fact that these configurations are complex. There's some parameter, either the metric or some other parameter, which becomes complex. Okay, but there's a family of solutions. You can think of this as some small temperature deformations, but remember that it's still supersymmetric. Okay, and here at infinity you have some background value of this R symmetry gauge field. And then there's flux of this gauge field in the interior, and the tip, by the time you reach the tip, this Wilson line vanishes. Okay? So that this geometry is smooth, the fermions are perfectly antiperiodic as they should be, and because there's this extra gauge symmetry Wilson line, these are also supersymmetric. Okay? Then you can calculate the action, the on-shell action of gravity on such configurations, and what you find, the black hole contribution is defined as the limit. What you find is that the action is actually independent of this deformation parameter, as you might expect from an index, and so there's a smooth limit. Okay? And then this was extended to various ADS spaces, including by people here in the audience. And then in this nice paper, Luca and Joaquin and Murat Koluglu realized that you can do exactly the same thing also in flat space, asymptotically flat space. Okay, so there might not be an a priori notion of holography, but these kind of configurations exist. Okay, and that's what I'm going to. So Luca will talk about this more in his talk, but I'm going to pick up such a configuration and try to work with it. Okay. So let's take this thing. So I'll work with asymptotic R4. So you have ADS 2 times S2, and you have this kind of a geometry. And now the black hole sort of lives near the tip. You have to take this t goes to 0 limit, and then sort of isolate this ADS 2 times S2 configuration. Okay, so something like that. So at t equal to 0, you really have good old ADS 2 times S2. This is a thing that has been worked on a lot. For instance, Sen has a series of works on how to define sort of quantum properties of the system, or even much further back, the attractor mechanism. This is the context. You have some asymptotic flat space, and then you have some near horizon ADS 2 times S2. Okay. So you can decouple this ADS2 times S2 by taking t equal to 0. But in fact, if you do that, you also see that theory, you will see, as I will show you, also asks to be regulated. Okay, so you can either start with this regulated geometry and then take a limit, or you can directly work in the near horizon, and then there's something that goes suddenly wrong, and you'll have to regulate and come back. Okay, so that's the sort of historical route, and that's the route I'll take now. Okay, so we'll start with this ADS2 limit and consider a small deformation. Okay. Okay, so the next few slides are a sort of review of older work, so I'll be very quick, but there's also some new progress here, but I won't focus on that. So in this ADS2 times S2 geometry, you can now sort of ask for these localized integrals. Okay, so you have to find some off-shell configuration, you have to find all the solutions of these localization equations, calculate what's the action. There's a lot of things here which I don't want to discuss. I've talked about it in the past many times. And then you have some one loop calculation. So there's some new progress here, but at the end of the day, you get some formula for this localized integral on this ADS2 times S2. Okay, and the formula looks like this. Well, I'll take this one example of the 1/8 BPS black hole in n equal to 8 string theory. Okay, so you write this as some effective n equal to 2 supergravity. In fact, even here there's a bit of progress. So earlier we used to do some truncation, but now we can sort of treat the whole supergravity. There's also some technical progress. We learned how to deal with this kind of gravitini multiplex of shell and things like this. Let's just go on. You write a pre-potential for these vector multiplets, and then you calculate the one loop fluctuations for all the. So the vector multiplets are the ones which participate in the black hole solution. Okay, the others are classically 0, but you can ask for one loop determinants. Okay, the pre-potential in the n equal to 2 language for these vector multiplets is tree level exact. This is an old non-renormalization theorem because these theories are type 2 string theories on a torus, on a 6 torus. So there's fermion zero modes, which says that this is tree level exact. And so calculate this integral, the whole path integral reduces to a one-dimensional integral. That's the localized integral, which you can recognize as some Bessel function. Okay, so that's the sort of gravitational index, and I want to compare this with the string theory index. So in string theory, you can go back to weak coupling and just count how many states there are. That's the usual trace definition, and that's this microscopic index. Okay, this was done a long time ago for these black holes. And the answer is known. The index, the trace index trace, is known to be a coefficient for certain modular form. Okay, so here's this comparison. This is sort of n. N is some combination of the charges, which tells you how big the black hole is. This is this microscopic index, and this is this gravitational index. I put a superscript 1 to denote something that I'll discuss in a second. Okay, so you can see that you get very close to these integers, and you get exponentially close. So if you think of this gravitational index formula that I just presented as the sum of all perturbation theory around the ADS2 times S2, so all perturbative fluctuations. Okay, so the question is, what about non-perturbative effects? And so in order to do this, we have to sort of understand the number theoretic structure of these numbers a little bit. So this plot is the same data that I showed you in the table, but now I'm showing this on a log plot. So that's n, which is called delta here in the paper, and this is z, which is called w. So these dots, these blue dots, are the microscopic numbers, the discrete numbers. This dotted line is the sort of exponential of the Bacon-Stein-Hawking entropy, just as a reference, and you can see that there's a big difference in the log plot. The red dotted line includes a one loop correction, so you get closer to the exact value, but there's still some gap. And this blue line is this sum of all perturbation theory that I just presented. Okay. So on this plot, you can not see a difference between the blue line and the dotted and the dots. Okay. So that's the statement that is exponentially close. Once you get there, I can remove the log plot and show you a real plot of the difference between these two. Okay. So there it is. That's the difference, and you see indeed that you see the exponential correction. So even to get a difference of like 1, you have to go until order 100 or something. Okay, so that's what we are now after. Okay, we want to calculate this little difference. Okay, Now, yeah.
In the last one, in the last table, this was the degeneracy that's function of n. But
Yes.
do the degeneracies also have charge dependence?
So n is the charge. N is some combination of the charges. Yeah.
Okay. In the next one, I should understand delta has the charge now.
Here, n is called delta and z is called w. This is from the paper, and we just changed notation. That's all. It's exactly the same thing. Yeah. Yeah.
So there are no higher derivatives, correct?
Yeah. So okay. So you can see that in this formula. So if you go back to this action, what is it? There. Okay. There's some action of gravity. This, when you start, you should write a full derivative expansion. Okay. So now you have some n equal to 2 configuration. So you can write the analog of f terms and d terms for n equal to 2. So these are full superspace integrals and, sorry, chiral superspace integrals and full superspace integrals. The chiral superspace integrals are governed by the holomorphic prepotential f, and the full superspace integrals are the analog of d terms. So in this paper with Valentin, we showed that these d terms don't contribute. Then there's a question of what are also, the f term also has an infinite series, but because of this non-renormalization theorem for the type 2 on the torus for n equal to 8 theories, this truncates. So in general for Calabi-Yau, this will be a full function, and you'll get some OSV type formula. That's the formula we got with Atish and João. Yeah? Yeah.
The one loop determinant involves the full supersymmetry action, right?
Good. So the one loop determinant, if you remember the localization formula, doesn't depend on the physical action. So the way, if you remember your localization, how to do it, you start with some path integral, then you deform it by some q exact term that you can choose, and the one loop determinant is of that term. That also, we had to work very hard to calculate that one loop determinant, and so there's, in fact, there's many more references here, many people have contributed, and now finally, so in these papers we sort of essentially got the full one loop determinant. There was something missing that we finally nailed down with Luca and Joaquin. That's exactly where I'm going. Okay, so what is missing is that there's some subtle effects coming from precisely this regulator that I talked about. Okay, and this is known to almost all of you here in the audience, I'm sure. It's been discussed a lot in the last few years under various guises, JT gravity, the Schwarzian mode, etc., etc. But I want to sort of take a self-consistent point of view and keep going with this ADS 2 times S2. Okay. So now let's go to this number theoretic formula. So because you have these numbers are coefficients of a modular form, there's a beautiful formula which writes this integer as a sum of analytic functions. Okay. So this is c goes from 1 to infinity. This is c to the minus 9/2 for this particular function. Kc is some Klostermann sum. It's a sum of phases over rational points. That's a very typical signature of number theory, of some sum over rational points. And I is some modified Bessel function. Okay? Remember that the I Bessel function goes as exponential, and so you can see that the c equal to 1 term is exponentially dominant over the higher c terms. Okay? So this is sort of given to you by the number theories, and what we have so far is that we've captured all of this Bessel function by summing the perturbation theory. Okay. So now the question is, what about this? Okay. So already in 2014 with Atish and João, we understood what the structure of the sum is. This in gravity, and these are some orbifolds of the full ADS 2 geometry embedded in the string theory.
Yes. First thing, you included the Schwarzian.
So far I didn't say anything about it, and it worked, and you'll see why in a second. Okay. I'll answer that in 2 minutes. That's what I'm just going to answer that in a second. Yeah. So the answer is yes, but you sort of don't need it. Yeah. Okay. So what you expect is that, so here I just copied this formula. Think of this as the contribution of the orbifold, ZC. C to the minus 9/2, I write as 1 over C to the 7/2 times 1 over C, Klostermann sum and the Bessel function. Okay. So this Klostermann sum, we'd understood as some contribution of a Chern-Simons theory which appears in this near horizon geometry in the full ADS2 times S1 times other things. And then we need to do, so you can try to sort of rework this localization, okay, on this orbifold geometry. When you do that, what you find is that you get exactly this much. Okay, so when you sum up all the quantum fluctuations of the bulk modes, you get precisely this. Okay. So that means that there is this 1 over c which is missing, which you couldn't have seen at c equal to 1. So that's what is going on. Okay, so it's a very tiny effect. Okay. So what goes wrong? Well, there's a subtlety in this path integral, which you can also see directly from the from the theory itself. The theory knows about it. So if you do harmonic analysis on ADS2 times S2, you see that there are a special set of modes, which I'll call zero modes, which appears only in ADS2. So Camporesi and Higuchi worked out for various ADS and spheres. For ADS2, there's something special, that there are these formally pure gauge configurations. So it looks like d mu of lambda, but that pure gauge parameter doesn't vanish at the boundary. Okay? Therefore, these are physical modes, because the ghost is not normalizable. That's another way to say it. Okay? However, their action is zero because they're pure gauge formally. So they have zero action. Okay? So the path integral is not well defined. So you have to, what you really have to calculate is some kind of volume of the space of these modes. Okay? Now these modes are very important. So even in Ashok's calculations, these modes, they contributed a finite fraction to the leading logarithmic correction to the Bekenstein-Hawking entropy. And the way Ashok did it was, he said, assume that this integral is somehow well defined, and then you ask what happens if you change the size of the ADS space a little bit, and then using some ultra locality argument of Witten, you can say what's the contribution to the log correction. Now we want to do a full quantum treatment. So in order to do that, you need to do this regularization. Okay, so you start with ADS2 times S2 and give this a small temperature in this supersymmetric sense. What you find is that, so this is ADS2, and in the near horizon geometry you have an ADS2 times S2, and the size of the S2 is constant throughout the ADS2. When you turn on a temperature, you see that the size of this S2 grows as you go towards the boundary. It's a very funny behavior. When t is 0, all modes decay towards the boundary, okay? Except this one funny zero mode, which is kind of non-localized. And that mode starts growing, it explodes exponentially. Okay? Now you can isolate this mode and just plug that mode into the supergravity action. It's essentially Einstein-Maxwell type of an action of 4 dimensions or 10 dimensions. And what you find is that the action of that mode is precisely the Schwarzian. Okay? So you don't have to posit anything, just really comes out of Einstein-Maxwell theory. Yeah? And that has been, understood in great detail. So what the T does is to regulate the zero modes. It gives them a small mass, yeah? And you can take this regulator and calculate the path integral, and then take the T goes to 0 limit. So we borrow these results. So there's a point of philosophy here. So we know what this Schwarzian mode is. So we know that in CFT1 there is a 0, the Hamiltonian is 0, so there's a time reparameterization invariance, and when you break that, so ADS2 breaks it to just some SL2, as we heard yesterday in Christian's talk. ADS2 breaks it, and so Goldstone mode is the Schwarzian mode. Yeah? Now in most of the discussions in the last few years, people have explicitly broken this by small temperature because that's what they were interested in. They wanted to compare with some SYK model, so some near ADS2, near extremal theory. Here we want the effect of spontaneous symmetry breaking. We're interested in the supersymmetric ground state itself. Yeah? But it's like how for a magnetic field, if you want to calculate the effect of spontaneous symmetry breaking, you can turn on some explicit breaking, calculate it, and then take the explicit breaking to 0. That gives you the answer for the effect of the spontaneous symmetry breaking. So that's what we're doing. We're calculating with T non-zero, and then taking T goes to 0 to get the answer, right? What the result is, so you can see already here, this mode itself is very big, so the quantum fluctuations are also very big, so there's a good chance that there's a residue left at T equal to 0. Okay, and that's what happens. In fact, you can do this for generic extremal black holes, and what you find is that generically for non-supersymmetric black holes, there's no so the t goes to 0 limit for the effective action is singular. So the partition function vanishes. Okay, you get some positive power of t in front of the partition function. Okay, that is interpreted as saying that there's no mass gap for these generic extremal black holes. But for supersymmetric black holes, the t goes to 0 limit on ADS 2 just gives 1. And therefore there is a mass gap you can calculate, which is the order of 1 over the entropy to some power. Okay, so that's the first result. That's for ADS 2 times S2. This was the question that was asked. So basically the old calculation goes through as it is. And now you can repeat the calculation for the orbifolds. So you also have some Schwarzschild mode, and that gives you precise, the volume of the Schwarzschild mode is precisely 1 over c. Okay, so that sort of finishes this calculation. I'm almost out of time. I want to show you in one slide the status in higher dimensional ADS spaces. Okay, so the structure is very similar. Okay, there's been a lot of progress on this in the last few years. You calculate some superconformal index, and you can write it not as, so we're not yet there, but there's a formula of the following sort. It's a sum over saddles of some effective gravitational action at each saddle. Okay, and the sum over saddles are actually sum over rational points. So there's some number theoretic structure. And I'll sort of go over all the points. So there's many references. If I missed anything, please tell me. So firstly, directly from the index, you can try to calculate the saddles. This is similar to the Rademacher expansion, the Hardy-Ramanujan-Rademacher expansion. Now you can just ask, what is the saddle point of the index itself? So here we're in good shape. We can calculate the saddle points of the index. Okay, so this is in Super Yang-Mills theory, 4-dimensional Super Yang-Mills theory. This is some recent paper on ABJM theory. So in all these cases, you can calculate it, you get a structure of this sort, and you can calculate this exactly. Then you want to interpret this in the gravitational theory as some orbifolds. Here, so I'm going to talk about things which are sort of less and less understood. So here again, we understand something. So this is a paper in ADS 5 where they understood the structure as a sum over orbifolds in type 2B string theory. In ADS 4, we recently understood how to understand these saddle points as orbifolds in M theory, 11-dimensional supergravity. ADS 3 and CFT2 were already kind of known earlier. Then there's a 1 over n expansion. Here it's much less understood, but there are certainly hints. So this works in various ADS spaces, but sort of my hope is that eventually we'll learn how to calculate these things also in gravity. And then finally there's this number theoretic structure, which is very mysterious beyond 1 or 2 dimensions, because there's no modularity really. There's an S1 times S2 or S3, but it seems that there is some underlying sort of broken modularity or something like that. Don Zagier calls this quantum modularity, which might underlie these kind of functions. Okay, so that so these are the 4 points. I thank you for your attention.
Thanks for a very nice talk. Questions?
Sorry, I should have referred to your work.
I mean, the last point you said is broken modularity, you meant SL2?
Yeah, so let me just also refer to your work just now and answer your question the same. So here by modularity, I always mean SL2Z. Okay? And there are, for those of you who don't know, there are works on sort of some type of modular invariance using SL3Z. Okay, Whaley and friends have been going down that route. But I think that's not, so that doesn't inform you about this kind of a structure. Okay, it's useful for other things. So here I sort of, this structure over rational points C and D is specific to SL2Z. Okay? And what happens in the SL3, so this is an old, I forget who did it first, there's an observation that there's an SL3Z modularity in CFT4. Okay, and I think this was Felder and Varchenko, and sorry? No, but much before in the mathematics literature, this was observed, Felder and Varchenko and some others. And then this was picked up by various physicists. Shlomo, Abhijit Kadde has worked on this, Whaley and friends have worked on it. But what that does is relate one theory to another. Okay, you can work out the physical consequences of this mathematical symmetry, but that's not what is going on here. If you try to take that SL3 set and force it to sit on one theory, you get a singularity. It's not useful.
So yeah, another question. So the Kloosterman sum that you mentioned earlier, so you also don't see this appearing for the SL3Z context, right?
You should tell me, but I think you should tell me. I think the answer is no.
Do you expect a full 1/n perturbative expansion around each saddle, or do you expect that to truncate for these supersymmetric cases?
So I think that depends on the theory. So for instance, what I expect is that you should be able to sum this up into a function. Now it could happen in two ways. It could either be some infinite asymptotic series of a certain function like the Bessel function like we saw, or it could be like what Nicola is going to talk about, I hope, later today, where this thing truncates and then it's just some Laurent polynomial. That I don't have an a priori expectation for what will happen. It also depends on the degree of symmetry, right? In ADS 5 you have a lot of symmetry, so there's good reason to believe that truncates. But ADS 5 times S5, I mean, that's highly supersymmetric. But in general, if you have ADS 5 times some other n equal to 1 type of theory, then I don't know whether it's going to truncate or not. But my belief is that it's a well-defined object that you're calculating. Shota? No.
Maybe sure.
Okay. Well, it's okay.
Thanks for the talk. Could you have anticipated these powers that they go with the 1/c expansion, 9/2, 7/2, and made perhaps a different argument for the fact that this zero mode gives just 1/c to power 1?
Sorry, I'm not sure I understood the question. So the fact that there's this 7/2, etc., I can go there.
You have some rational powers like c over 7/2, 9/2.
Yeah.
So could you have made a different argument for the?
A priori, could I have guessed where these numbers are coming from? So as you know, these numbers are coming from sort of the details of the modular symmetry. In this case, it's the modular weight of the modular form. I guess your question is, do I know where this comes from in gravity? Is that
yeah, that's the same for if you take the leading expansion for E tilde, that's the same
exactly.
as in front of
So here you see that's it. So in fact, you can do a change of variables, so you can absorb this 7/2 completely into this.
Yeah.
Okay, that comes from the number of it's the matter content of the gravity. But there's still one mode, which is this zero mode with some mass.
So is there any like a Hilbert space interpretation of the formula? Because if you just have the black hole saddle, then like a left and right Hilbert space don't factorize. But in the end, like by summing up all the saddles, you got the integers. So which means that you have like eventually have some trace interpretation. Yeah, so that's a great question. So I started my talk by saying we don't have a good Hilbert space interpretation of gravity. I should have put a caveat, but I didn't have time. I mean, I put it yesterday, but then I removed it because of time. Of course, there is, not of course, as we've heard, as we have learned, that statement also can give, it might, when the gravity is at some, free tensionless point, as you might hear. But, in my life, I'm hardly ever free, and I'm hardly ever tensionless. So we will, this we should wait to hear from the experts who have achieved such a state. But what I'm saying is that in the usual gravitational variables, so when you have some sort of small Newton's coupling and so on, I don't know at all how to make sense of a Hilbert space. Okay? But there might be some quantum gravitation. I mean, we hope there's some quantum gravitational Hilbert space. So that at that point, the counting at that point is related to things like giant gravitons and stuff like that, things we've talked about. Okay? So it could be that there is in ADS 5, there's also counting which should really happen at some tensionless point. But if you're doing BPS counting, you might be able to get away even by counting giants and things like that, and their fluctuations.
Sorry, related to that question, in ADS5, if we move to ADS5, there's this 5 parameters. There's some evidence that there's a 5 parameter set of supersymmetric black holes, including, I'm talking about the Santos and friends, including a charge condensate. And somehow the only thing that's playing a role here is this 4 parameter set.
Yeah.
I was wondering if there's some role for these additional solutions in the story.
I don't know. I don't know if these are, so that's my short answer, I don't know, but I also, maybe you can explain this to me. Are these really supersymmetric solutions?
As you probably know, I mean, the only constructions of them have been numerical.
Yeah.
They've been constructed as non-zero t, and then t goes to 0, limit is taken, and the claim is that they are supersymmetric solutions. That
yeah, so it's very likely they're extremal. That's what you would see from.
The claim is they obey the BPS bound.
Exactly. That's sort of an extremality condition.
No, BPS bound. The BPS bound. So they're supersymmetric.
There's a nonlinear BPS bound which that's very.
Energy is equal to charge plus charge.
That's not how the BPS bound in ADS5 is, as you know. Remember, it's a more nonlinear.
No, it's energy is equal to r charge plus angular momentum.
Maybe you can explain this to me later.
Yeah. If you think about embedding this into string theory, wouldn't there be a tachyon from the orbifold fixed point that destabilizes these?
No, these are supersymmetric. So what happens is locally these are C2 mod Zn orbifolds and supersymmetric ones.
So
Go on.
So there is a full classification of all the gravitational saddles by just solving the localization equation for the higher dimensional?
Not quite, but maybe Luca will talk about this more in his talk a little bit. Yeah. So that's not yet sort of a theorem. So in the old days, what we just, with Atish and João, we just sort of identified the things. Okay. Luca and Joaquin and friends had more arguments to say why a whole class of essentially non-supersymmetric orbifolds don't contribute. Okay. Now, there is this question of what are the supersymmetric orbifolds there are, and in this context, sort of, if we say that the only things we know are the ones which live in string theory, then okay, maybe we can put it all together. That's the status, at least as far as I'm concerned. No? Christian?
Yes, no? All right. Well, in view of time, let's thank Sameer again.
Thank you very much.